I'm going to start this video with a demonstration, right? A very simple demonstration. And then in this video, we will discuss what we observed during the demonstration. Uh, I have this scale with me, right? And the other object that I have is an orange, right? And I have a rubber band attached to this. I'm going to make a system out of this. I'm going to just insert this scale over here, and I have this system over here, which consists of this scale and this orange attached to its end. What I'm going to try to do is that I'll identify this end, right, this end over here as the axis of rotation. So I'm going to hold it over here, right, and what I'm going to try to do is try to rotate it in this direction, right. From my side, it's going to be the clockwise direction. So I'm trying to rotate in this clockwise direction, right, and as you can see over here, I'm struggling to do that, right. Right, let me try that again. So as you can see, I'm struggling over here. My muscles over here are, getting stressed, right? You can see the scale bending over here, and I'm trying hard, but I'm finding it very difficult to rotate it, right? Finally, I have managed to do that, right, to some extent, right? Okay. Having done this, now let me do what I'll do is I'll shift this orange a little bit towards here in this direction, and again this I'll keep as the axis of rotation, and I'll try to rotate this. And as you would have guessed, and as you can see over here, I'm finding it easier to rotate this. I'm finding easier, even though the mass of the system has not changed. I'm using still the same scale, the same orange, but I'm finding it easier to rotate this. If I move it further down over here, I'm finding it still easier to rotate this, and in fact I'm able to rotate it quite easily, right? And if I bring it very very close over here to this particular point, it becomes still very easy, and I'm able to rotate it quite easily, in fact, right? So what we have observed in this is that even though the mass of the system remained the same, right, the amount of torque that I had to apply, the amount of force that I had to apply over here at the axis of rotation at this particular location kept on changing as I shifted this orange from the left to the right, right? And now you would have probably guessed why this is happening, and all of us have experienced this, right? What's the reason why is this happening, right? The reason is why this is happening is because of something known as moment of inertia, right? And moment of inertia is the physics explanation for this, right? A layman would be able to explain it easily that the mass is shifting towards the axis of rotation, and therefore it becomes easier. But let us look at it from a physics perspective, right? Moment of inertia, right? For that we need to understand what inertia is, right? I'm sure you would have seen the video on Newton's first law of motion and the concept of inertia. If not, I would encourage you to do that before you watch this video, so that you are able to connect between inertia and moment of inertia, right? Okay, what is moment of inertia? To put it in very very simple words, moment of inertia, let me write over here, moment of inertia is inertia associated with rotational motion. Okay, that's a very very simple explanation of moment of inertia. So basically moment of inertia is inertia, right, as we had discussed or understood it earlier. But when a body is performing rotational motion, instead of using the term inertia, we use the word moment of inertia, right? So let us once again very quickly revise what was inertia. So in inertia, what we said is that basically it is, if I were an English language teacher, I would call it reluctance to change, right? I like this phrase to describe inertia, reluctance to change, right? From a physics perspective, I should be more specific. I should say reluctance to change state of rest or motion, right? This is what inertia is, right? And this is what Newton's first law of motion is all about: reluctance to change state of rest or motion, right? This was when the body was performing translational motion, right? Will remember there was discussion on, let us say we have a body of mass 2 kilogram and another body of mass say 4 kilogram, and if I apply same forces on this, say 75 Newton and 75 Newton, we know this accelerates more and this accelerates less, right? Obviously because of mass, and which we say is because of the property of inertia, right? this has more mass, so it has more inertia, so it has more reluctance to change. So when we apply a certain force, this accelerates less because it has got more inertia, right? The same would happen if they were already moving with the same velocity. Let us say we are not applying any forces. Let us say this is moving with 10 meters per second. This is also moving with 10 meters per second. Now, for this object, if I have to stop both these objects, I would require a larger force, right? Because this has got more mass, therefore it has got more inertia, meaning that it has reluctance to change, meaning it is moving with 10 meters per second, it wants to continue to move with 10 meters per second, but since it has larger mass and therefore larger inertia, I would require a larger force. So that was what we discussed when we discussed inertia in translation motion. Same thing happens when a body is performing rotational motion, right? As you saw in the demonstration that we did, the system was trying to do rotational motion, right? And in that case, we use the word moment of inertia. Moment of inertia. Right? In principle, from a concept perspective, both inertia and moment of inertia are same. But as I said, this is with translation motion, this is with rotational motion. And if you go into the depth of it, there is a difference between inertia in translation motion and moment of inertia, and that's what we demonstrated that's what we demonstrated when I took this example or took this demonstration of the scale and the orange. What we observed in the demonstration was that the amount of torque required or the amount of force required, right, was dependent upon not only on the mass, right, but it was also dependent on distribution of mass. Right? How is the mass distributed in the system? Right? When the mass was away from the axis of rotation, right? If I draw the diagram over here, this was the scale and this was the orange over here, right? I was trying to apply a force in the upward direction. I was trying to rotate it in this direction. When the mass was over here, I had required a huge force, a large force was required, right? But as I kept on shifting it over here in this particular direction, lesser and lesser force was required, right? Or lesser and lesser torque was required. What we conclude from this is that if more mass is distributed or placed away from the axis of rotation, larger force is required. And that would mean that more moment of inertia. Now, this is a very important point. If more mass is distributed away from the axis of rotation, more moment of inertia. Right? So, it does not depend only on the mass, it also depends upon how the mass is distributed. Right? If I bring the orange over here, right, I require less force, right? Because the moment of inertia has decreased, the mass has come closer to the axis of rotation. Right? Another thing that we have to keep in mind while we discuss this example was that the system was at rest. Right? The system was at rest and we were trying to move it. Right? So in this case, we found more moment of inertia. Right? Let us assume a scenario where the body is already in motion, like we took here the example of the two bodies in motion with same velocity. Right? Let us take an example of that. For that, I'll take a slightly different example. Let us say we have a disk. Let us say we have a disk, right? And these are the shafts of the disk, and let us say we are trying to rotate it, right? And we have this disk of the same mass but slightly different arrangement, right? So let us say we have, let me see if I'm able to get my drawing correct. Yes, we have the same disk, right, but slightly different arrangement. Let us say we have some, right? Okay, right. So we have disk A and disk B both having same mass, right? So let us say this is of 12 kilogram, this is also of 12 kilogram. But the difference, as you can see over here, is in the mass distribution. Here the mass is distributed uniformly. There is some amount of mass closer to the axis of rotation, whereas here the mass, there's no mass near the axis of rotation. The mass is all on the periphery, right? It is away from the axis of rotation. So when I rotate this with the same torque, what will we observe? Right? Well, I'm sure you would have guessed that this would continue to rotate for a longer time because it has got more moment of inertia. Here it's got less moment of inertia. Right? because the more mass is away from the axis of rotation, whereas here the mass is distributed uniformly and there's a lot of mass near the axis of rotation. So more moment of inertia, less moment of inertia. In fact, if both of them are rotating with the same angular velocity, this would require a larger force to be stopped. This would require a less force to be stopped. That is again because of more moment of inertia in this case. And therefore, when we look at the practical application of moment of inertia, we can take the example of a bicycle wheel. Right? The bicycle wheel is something like this. Right? Right? We have spokes over here, right? And all the mass is on the periphery. It is away from the axis of rotation because we want more moment of inertia. With when we apply a force, we want to continue to rotate for a longer time, right? And therefore, all wheels generally have the mass distributed away from the axis of rotation. With this, I think you have got idea about the concept of moment of inertia. What we will do in the next few minutes in this video is look at how do we get the magnitude, or how do we look at the mathematical aspect of moment of inertia. Right? If I take the example of a three particle system, right? Let us say this is the axis of rotation, and say we have another mass, and there is mass number 3, and let us say masses are 2 kilogram, 3 kilogram, and say 1 kilogram, and let us say the distances are, say this is 2 meter, this is even though it is looking 2 meter, this is 1 meter, and this is say 4 meter from the axis of rotation. So we got three masses of mass 1 kilogram, 3 kilogram, 2 kilogram, and these distances. And the moment of inertia of this three mass system is obtained by, moment of inertia denoted by I will be obtained by m1 r1 square plus m2 r2 square plus m3 r3 square. What we do is we multiply the mass to the radius square, or the distance from the axis of rotation, right? As we discussed earlier, moment of inertia depends not only on the mass but the distribution of mass. So therefore we get m and r both in the equation. So if I do a quick calculation over here, I'll get mass 1 into 2 square plus mass 2 is 3 into 2 square plus 1 into 4 square. That would give me 4 plus 12 plus 16, right? And that would give me 32, 16, 20, 20, 30, 32. This is kilogram, this is distance, so kg meter square. So 32 kg meter square is the moment of inertia of this three mass system, right? So this is how we calculate moment of inertia. For ease, I started with a very simple example of a three mass system, but generally we will not have things like this. We'll have a system like this, wherein the mass is uniformly distributed. So in this case, what we do is we look at very, very small particles of mass m, right? And we take their distances from the axis of rotation and calculate the moment of inertia. So in such a case, right, the formula for finding out moment of inertia would be sigma of mi ri square, I is equal to 1 to n, because there would be n number of particles over here distributed at different points from the axis of rotation. So I would take each particle, take its mass, multiply it with distance squared from the axis of rotation, and I would do that for all the particles, and that would give me the moment of inertia of this entire body. Okay, to end this video, last point, that the question that would be coming to your mind, right, would be this. Let me. I don't want to go to the next page. I want to complete it over here. So maybe I'm having shortage of space, but I'll try to manage it over here. The question that must be coming to your mind is, if moment of inertia depends upon mass and radius, why are we having mri square or r square in the equation? Why not simply mr? Right? The reason is mr square can be looked as mr into r. Right? Mr, right? This is mass, and if you multiply it with g, you will get weight. So this is force into displacement. So this is torque. This can be thought of as torque. Right? It's not exactly torque, but it can be thought of as torque. This is a weight. This is the distance from the axis of rotation. This is torque, and this is the axis of rotation. So I'm multiplying. Basically, I'm multiplying the torque, which is the force or the equivalent of force in case of rotational motion. In translation motion, we have force. Right? In rotational motion, we have torque. So this is torque multiplied by distance from axis of rotation. So what we're trying to find out is basically torque at each point, and what is the distance from the axis of rotation. So if I look at this particular point, this particular particle has a mass, therefore it has a weight. So it is applying a torque, and what is the distance from the axis of rotation of that particular torque, or the torque applied by this particular particle. Similarly, I'll take another particle. What is the distance of the torque applied by this particular mass, and therefore I get mr into r, and that gives me the moment of inertia. Right. I think you have got a good idea about what moment of inertia is. In the next video, we will look at radius of gyration, which comes out of the concept of moment of inertia. Thank you.